Welcome to class for 7.2, textbook section 5.2, part 2. We're going to continue our study of the formulas we worked on last class. So notice how over here I just did a quick copy and paste of those formulas. I recommend you do the same, just so we have them for reference. Okay, so let's look at example 5 here. Suppose that sine alpha equals 12 over 13 for a quadrant 2 angle alpha. That's important. What we're going to do is draw a triangle in quadrant 2, because that's what it says. There's a quadrant 2 angle alpha right there, and sine is 12 over 13, so I'm going to write 12, 13. Do your Pythagorean theorem, that's negative 5. We keep reading. Sine of beta is 3 over 5 for a quadrant 1 angle beta, so let's draw a second triangle. That's quadrant 1, that's beta. Sine is 3 over 5, which means adjacent is clearly 4. And now we're going to use those triangles to figure this out. So A, cosine of alpha. So look at your alpha triangle. That's just negative 5 over 13, because that's just adjacent over hypotenuse. Now B, cosine beta. Same thing. Do A over H, 4 over 5. So A and B, pretty easy. Now for part C, it says cosine of alpha plus beta. Remember here we have to use our formulas. Hopefully you've memorized at this point. Cosine alpha, cosine beta, minus sine alpha, sine beta. Now look at your triangle. Be very careful as you're plugging it in. Cosine alpha, that's negative 5 over 13. Cosine beta, that would be 4 over 5. Sine alpha is 12 over 13. Sine beta is 3 over 5. We multiply, that's negative 20 minus 36, all over 65, and look at that. Negative 56 over 65. Done. Okay, now part D, same thing. We're going to do sine alpha cosine beta plus cosine alpha sine beta. Let's work this out. So sine alpha, that would be 12 over 13. Cosine beta, that would be 4 over 5. Plus cosine alpha, that's negative 5 over 13. And then sine beta is 3 over 5. We multiply, that's 48 minus 15 over 65. That is 33 over 65. We are done. Okay, E, tangent of A plus B. So again, use your formula. Tan A plus tan B, all divided by 1 minus tan A times tan B. Plug it all in, so tan A, that's negative 12 over 5, plus tan B, that's just 3 over 4, all over 1 minus negative 12 over 5 times 3 over 4. Now when you're doing this, it's really important that you want to start here. People have a hard time with fraction work, so do this first. So leave the top alone. Negative 12 over 5 plus 3 over 4, 1. This is going to be plus 36 over 20. Now we do that because now it's going to be easier to do our fraction work. Multiply everything by 20 over 20. And then we're going to get negative 48 plus 15 over 20 plus 36. And there it is. Negative 33 over 56. There's our answer. Now here's a pro tip. If you look at part C, D, and E, they're actually linked. If we simply did 33 over 65, this one, divided by this one, the cosine one, negative 56 over 65. Notice how we get the same thing. Checks out. And that's, again, because sine of theta over cosine of theta is, in fact, tan theta. So you could use that in your homework as well to save yourself some time. Okay, 2 more examples. So here we have another triangle question. Again, this looks difficult, but it's actually not that bad. Call this thing alpha, call this thing beta. So really we can rewrite this as sine alpha minus beta. Use our formula, sine alpha cosine beta minus cosine alpha sine beta. And now you just got to think, well, where are these triangles? Well, hopefully you recall your inverse trig ranges. Remember, cosine is 1 and 2, sine and tan are 1 and 4. And again, that's your inverse trig ranges. So our alpha triangle, that's going to be negative 4 fifths, so that's going to be quadrant 4. That's our alpha. This is 3. And our beta triangle is positive, so that got to be in quadrant 1. That's just 3, 4, and 5. And then from here, it's pretty much the same thing we've been doing. Sine alpha, that's negative 4 fifths. Cosine beta, that is 4 fifths. Minus cosine alpha, that would be 3 over 5. Sine beta, 3 over 5. Negative 16 minus 9 over 25, that reduces to negative 1. Okay, last example. This one probably looks the craziest, and it's a little heavy on the algebra. So let's try it. Let's call this alpha, let's call this beta. So really we're looking for tan of alpha plus beta. So I'll just write that for you. Tan alpha plus tan beta all over 1 minus tan alpha times tan beta. And we gotta make some triangles here. So we can assume the variables are in quadrant 1 just to make it simpler. And on a test or quiz, I would state that the variable is in quadrant 1. That makes it much easier to work with. So let's call this alpha. If sine inverse of x, think of that as x over 1, which makes this one the root of 1 minus x squared. You just use the Pythagorean theorem there. And then the beta triangle, we're going to do something very similar. Think of that as y and 1. So this must be the root of 1 minus y squared. And again, that's just through the Pythagorean theorem. Now comes the part where we got to plug it in. So tan of alpha, that's x over the root 1 minus x squared. Tan beta, that's root 1 minus y squared over y. Divide that by 1 minus the product. So it looks pretty messy. At this point, all we got to do is clear the complex fraction. So we're going to multiply everything by the common denominator, which would be y times the root of 1 minus x squared. And then we're going to leave it like that. And the book actually leaves it like that too. So the final answer, after we multiply, it's going to be xy plus the square root 1 minus y squared, 1 minus x squared, all divided by y root 1 minus x squared minus x square root 1 minus y squared. So pretty ugly answer, but that's a pre-calc level kind of trig question.